Let's look at how we typically interact with a language model. On the left, we send a text prompt and get a static response back. But on the right, a system is autonomously navigating a computer directory, checking files, and executing code without our input. This creates an illusion of agency. In reality, large language models are static probability engines, locked behind an API. They cannot inherently verify facts or execute code. There is a rigid barrier isolating the model's neural network from the external environment. Making a system autonomous does not mean building a larger or smarter foundation model. It requires a different software architecture to bridge that barrier. Autonomy is engineered by wrapping a static text predictor in a continuous programmatic control loop. In software terms, this continuous control loop is a standard algorithmic while loop that systematically executes around the model's API call. This loop architecture interleaves the model's internal reasoning with direct access to the external environment. Researchers formalize this architecture as the ReACT paradigm, short for reason and act. The defining rule of ReACT is strict. It explicitly forces the model to generate a text trace of its internal logic before it is allowed to commit to any physical action. To understand how this works, we have to break this continuous ReACT cycle down into its 4 foundational phases: perceive, think, act, and observe. This recursive state-tracking machine enables a language model to function as an active problem-solving agent. We open the execution loop with the perceive phase. For an AI agent, perception is not sensory input. It is structural context injection. The software wrapper injects 3 specific components into the prompt payload: the original user request, definitions of the available tools, and the historical execution trace. We then move to the think phase. If you force a language model to take immediate action, you run a systemic risk because it lacks a dedicated working memory space to plan. The mechanism to solve this is requiring the model to first generate a raw text-based reasoning trace. This internal monologue induces state tracking. It allows the system to update its action plans dynamically based on the context it just perceived. By generating this text sequence beforehand, the model can flag internal exceptions and catch its own logical errors prior to executing any external code. Precise analytical tone. Thinking in an agentic system is simply the act of writing tokens to a temporary scratchpad. This mathematically conditions the probability of the next output. This brings us to the act phase, where the model must make a structural decision regarding its output format. Execution splits into 2 paths. First, generating a tool call formatted as JSON. Emitting this JSON forces the inference engine to halt while the application layer executes the external API. Alternatively, if no external data is needed, standard text output breaks the loop. The language model itself never actually acts on the external world. It strictly formats structured instructions for a deterministic software wrapper to execute. The final piece of the architecture is the observe phase. This is the mechanism for feeding the external world state back into the isolated model. The system takes the raw output from the previous tool call, whether that is a successful database row or a Python error traceback, and appends it to the end of the context window. This graph tracks task trajectories. An ungrounded chain of thought naturally drifts into hallucination, but an observed chain of thought snaps sharply back to a rigid baseline when it hits an observe node, grounding the model with external state data and automatically re-triggering the perceive phase. This cyclic context update empowers the model to self-corrupt. If a previous tool call resulted in a syntax error, the model reads that error and tries a different approach. An agent's reliability is built entirely on this feedback loop's ability to recursively overwrite faulty internal logic with hard external data. Moving from ideal theoretical operation to reality in production environments, dynamic state machines are highly prone to compounding logic errors. The most common failure is a stuck state. Here, an agent traps itself by repeatedly executing the exact same failed tool call. Because API calls cost money, developers implement strict stopping conditions. The primary constraint is a maximum cap on loop iterations. The system severs the connection when that limit is reached. Another approach is dynamic pausing, where execution is suspended if the model's output confidence threshold drops below a predetermined metric. Developers also integrate human-in-the-loop checkpoints. These temporarily pause the autonomous cycle to demand human judgment when specific algorithmic blockers are encountered. Ultimately, engineering agentic systems requires a focus on defining boundaries and fail-safes to manage the inherent unpredictability of the loop. Beyond the model's loop, we have to look at the external tools themselves. This introduces the concept of agent-computer interfaces, or ACI. We invest massive effort into traditional human-computer interfaces, but language models require vastly different parameters and affordances than human users. In manufacturing, there is a concept called poka-yoke, or mistake-proofing. Engineers apply this directly to tool schema design for agents. When Anthropic built a coding agent to solve GitHub issues, they found the model frequently crashed when attempting to use relative file paths after navigating away from a root directory. Rather than writing a longer system prompt telling the model to be careful, they altered the tool definition to strictly demand absolute file paths. This specific ACI adjustment entirely eliminated that class of error. This highlights Anthropic's overarching ACES on production implementations. Successful autonomous agents rely on simple, composable patterns rather than dense, heavily abstracted development frameworks. Reliable agents are ultimately just deterministic execution loops wrapping probabilistic engines, governed by strict observation and meticulously engineered interfaces.